chemical equilibrium, the state, we can define it as the state where the concentration of reactants and products remain constant with time. Is called chemical equilibrium. Okay, so that is how we can define chemical equilibrium in simpler terms. So any chemical reaction carried out in a closed vessel will reach equilibrium. So if the reaction is carried out in a closed vessel, we'll reach equilibrium. So since no changes occur in the concentration of reactants or products in a reaction system at equilibrium, it may appear as though everything has stopped, but equilibrium is highly dynamic. Equilibrium is highly dynamic. Okay, just for example, if let's say 20 people enter into a hole, and at the same time 20 people come out. Okay, so the net change here is equal to 0. 20 enter, 20 come out. Okay, so in this case it doesn't mean that the situation is static, but it's highly dynamic. Okay, so but in chemical reaction, we use for a reaction which is at equilibrium, we use a double arrow, this one. Okay, so a double arrow is used to show that a reaction can occur in either direction. A reaction can occur in either direction. Okay, for example, we can write as A to B. A can form B, then at the same time B can form A. Okay, so we can now look at the equilibrium constant. The equilibrium constant, Kc. The equilibrium constant Kc. Okay, so we can consider a reaction. Let's say A plus B then forms C plus D. Okay, so this is the reaction. So we can write Kc expression as Kc will equal to the concentration of C raised to the power C, concentration of D raised to the power D, over concentration of A raised to the power A, concentration of B raised to the power B. Okay, so Kc Kc is a ratio. Kc is a ratio of the equilibrium concentrations of products over equilibrium concentrations of reactants, raised to the power of their stoichiometric. These are the stoichiometric, raised to the power of their stoichiometric coefficients. Okay, so this is the how we can write the Kc expression, okay, for a given reaction. So let's have an example. Write Kc expression. Example, write Kc expression for the following reactions. So A, we have N2O4, then forms 2NO2. Okay, so that's nitrogen tetraoxide. It forms 2 nitrogen dioxide. Okay, so we can write Kc for this one. This is the product, this is the reactant. So we can say Kc is equal to NO2 squared over N2O4. Okay, so the square brackets used in this expression shows that the concentration is in molar or more per liter. Okay, so we can have another example. Let's say ammonia, for ammonia gas, then plus 7O2, then is giving us 4NO2, then plus 6 water vapor. Okay, so we can write the Kc expression for this one. So say Kc will equal to concentration of NO2 to the power 4, water to the power 6, then over ammonia NH3 to the power 4, then oxygen to the power 7. Okay, so that is how we can write the Kc for this reaction. Okay, so now let's look at the characteristics of Kc. So what are some of the characteristics of Kc? Okay, so these characteristics are very important as we are going to apply them in our calculations. Okay, characteristics of Kc. The first one, equilibrium. Equilibrium can be approached from either direction. Equilibrium can be approached from either direction. Okay, now the second one, Kc does not depend on initial concentration of reactants and products. So Kc does not depend on the initial concentration of reactants or products. Kc does not depend on the temperature. Kc does not depend on temperature. Okay, then we now look at the magnitude. Let's look at the magnitude of Kc. So we shall use the magnitude of Kc to determine whether the reaction lies to the left or right, or there is no shift. Okay, so we can now look at the magnitude of Kc. Okay, so if Kc value is large, if Kc value, number one, if Kc value is large, if the Kc value is large, that is Kc greater than 1, Kc greater than 1 means the equilibrium lies to the right. The equilibrium lies to the right. So if it lies to the right, it means it favors products formation, or the equilibrium mixture contains mostly the reaction mixture contains mostly products. Okay, so in this case favors the product, since it lies to the right. Then the second one, if Kc value is small, if Kc value is small, that is Kc less than 1, it means the equilibrium lies to the left. Equilibrium lies to the left. So in this case, it means the reaction mixture contains most reactants. So in this case, the reactants are favored, or formation of the reactants is being favored in this case. Okay, there will be less products than the reactants. Then the third one, if Kc value is close to 1, so in this case it means the reaction mixture contains appreciable amount of reactants and products. So in this case, reactants and products, more like the products, the reactants will equal to the amount of the products. Okay, so now let's see how we can write Kc expression. Writing equilibrium expression. Writing equilibrium expression. Writing equilibrium constant expression. Writing equilibrium constant expression. Writing equilibrium constant expression. Okay, Kc. Okay, so Kc values are listed. Kc values are listed without units. Listed without units. Okay, so don't include units. Don't include units when writing Kc or when calculating Kc values. Do not include units when calculating. So don't include, do not include units. Do not include units when calculating Kc. Do not include units when calculating Kc. Okay, so we can have an example. So what we just do, you simply so if the equilibrium concentrations are known, simply substitute the concentrations into the equilibrium constant expression. Okay, example. So let's see how we can do this one. Okay, so for the reaction carbon monoxide plus hydrogen gas then gives us methane, CH4, methane plus water vapor, methane plus water vapor. Okay, so for this reaction now write or calculate. Let's calculate Kc. Calculate Kc from the following equilibrium, equilibrium concentrations. So in this case, the equilibrium concentrations have been given. So the concentration of carbon monoxide is equal to 0.0613 molar. Then concentration of hydrogen is equal to 0.18 1839 molar. Then concentration of methane is equal to 0.0387 molar. Then concentration of water is equal to 0.0837 molar. Okay, so the equilibrium concentrations have been given. So now how do we calculate Kc? We look at the equation given. So you write the Kc expression first. So you're going to say Kc in this case is equal to methane, C, concentration of methane, CH4, then concentration of water, then over concentration of carbon monoxide, then times concentration of hydrogen cubed to the power 3. Okay, so this equation it's already balanced. Okay, so you can see we have six hydrogens one carbon, one oxygen. Yeah, it's balanced. So now you simply substitute the equilibrium concentrations into the expression without units. Concentration of methane in this case is equal to 0.03887. Then concentration of water is 0.0387. Then concentration of CO2, of CO carbon monoxide, that is 0.0613. Then concentration of hydrogen, that is 0.1839 to the power 3. Okay, so you multiply on top, you cube this number, multiply, then you divide. So you are going to find your Kc as so in this case Kc will equal to 3.93. Okay, so in this case, since it's greater than 1, so it favors product formation. Okay, so we can have another example. Okay, so for the Haber process, another example. Example 2. Okay, we look at the Haber process. This one for the production of ammonia. Okay, so we have nitrogen plus hydrogen gas gives us ammonia. Okay, ammonia. So this is the equation, the reaction for the production of ammonia, which is an important fertilizer. So this reaction was carried out. At 150 degrees Celsius. The concentration of ammonia is equal to 3.1 times 10 to the power -2 molar. Then the concentration of nitrogen is equal to 8.5 times 10 to the power -1 molar. Then the concentration of hydrogen is equal to 3.1 times 10 to the power -3 molar. Okay, so now question number 1, we now calculate Kc for this reaction. Calculate Kc for this reaction at 150 degrees Celsius. Okay, so now to calculate Kc for this reaction, we need to write the equilibrium expression using the equation given. So in this case, Kc will equal to concentration of ammonia squared concentration of ammonia squared over concentration of nitrogen times the hydrogen concentration cubed. Okay, then now we substitute the equilibrium concentration of ammonia, which is 3.1 times 10 to the power negative 2 squared. Okay, then over concentration of nitrogen, which is 8.5 times 10 to the power negative 1. Then concentration of hydrogen, which is 3.1 times 10 to the power negative 3 cubed. Okay, so you square this number on top, then you cube this one, you multiply by that, then you divide. So you're going to find your case as so in this case, when you do the arithmetic, so case is equal to 3.8 times 10 to the power 4. So you can see in this case the case is very large, meaning that it favors the product formation. Okay, so this is our case. Okay, so now the second question, we need now to calculate case for the reverse reaction. Calculate case for the reverse reaction. Calculate case for the reverse reaction. So reverse reaction simply means ammonia is now the product, the reactant. So ammonia, so it will be ammonia forms nitrogen gas plus hydrogen gas. Okay, so if you write the case, in this case, it will be now, you can see the reactants have now become the products. So we are going to differentiate. So we won't say case, so we'll put a prime to show it is happening in the reverse direction. So case will equal to nitrogen, concentration of nitrogen over hydrogen cubed over ammonia squared. Okay, so you can see that for the original equation, this one was on top, these were down. So in this case, case prime is the reciprocal of case. Case prime is the reciprocal of case. So there's no need of even you substituting the concentration and start calculating. So you simply say case prime is equal to 1 over case. Okay, so since you have already calculated your case, so you are just going to calculate straight away. So you just say case prime is equal to 1 over case. So the case has been calculated already, which is 3.8 times 10 to the power 4. Okay, so which is equal to 2.6. You are going to get 2.6 times 10 to the power negative 5. Okay, so that is our case in the reversing direction. Okay, so we can again calculate, let's say we introduce some integer in the original equation. Okay, so calculate Kc for the reaction. Calculate Kc for the reaction written as we are now going to modify this equation. Okay, so the equation is now modified. So for the equation written as half nitrogen plus half nitrogen then plus 3/2 hydrogen, then forms ammonia. 3/2 nitrogen then forms ammonia. Okay, so this is the equation. Okay, so the coefficients have now changed. So in this case now, we write Kc. So in this case, we can now differentiate it. We write Kc double prime. So we are going to say Kc double prime. In this case, it will be ammonia, concentration of ammonia over concentration of nitrogen, to the power half, over concentration of nitrogen to the power half times concentration of hydrogen, then 3/2. Okay, so now we compare this with the original. Let's compare this with the original equation. Okay, so we compare with the original equation. The original equation, expression, we compare this with the original expression for Kc. Okay, so the one for Kc prime, we have gotten ammonia over nitrogen to the power half, then hydrogen 3/2. So let's compare it with the original expression for Kc, so which is written as ammonia squared over nitrogen, then hydrogen to the power 3. So to make these two expressions equal, you can see here it is squared, here it's to the power 1, here to the power 3, here there is a half, here 3/2. So if we do this, we introduce a half here to the power half. So this half times this, it will cancel, it will give us this. Okay, then half times to the power nitrogen, it will be this one, then half times this, it will be that. Okay, so now we can safely say that Kc double prime is equal to Kc to the power half. Okay, which is just the same as Kc double prime is equal to root Kc. Okay, so now in this case, we are now, since we know Kc, so Kc double prime is equal to the square root of Kc. So 3.8 times 10 to the power 4 times to the power half, so which will give us 1.9 to the power 2. Okay, so now if the reaction is reversed, the Kc prime is simply the reciprocal of Kc. Then if the original reaction is multiplied by some factor n to give the expression like this one, to give the expression the one we obtain in our part 3, then the equilibrium expression is simply the square root. So the Kc double prime will equal to the square root of Kc. Okay, so we can end here. Then the lecture continues in the next session. Then we'll start looking at homogeneous equilibria. Thank you.